the workshop on the detection and emergence of complexity in the context of artificial life. I'm very happy to welcome both familiar faces and new ones. In a nutshell, the aim of artificial life is to study the fundamental mechanisms of life, abstracted away from its particularities of its biological implementation on Earth, or a popular way to say it, it aims to study life as it could be. And again this year, we have a wonderful list of speakers that both do very exciting research and very diverse one. So yeah, here's the list. We have both people who work on discovering and designing very exciting new examples of lifelike behavior, as well as people who develop theoretical results that help to ground such examples in solid principles from mathematics and physics. And this year we asked the invited speakers to end their talks with one or more problems, open problems, that they find particularly relevant for the field of artificial life. And hopefully this will inspire a lot of discussions. The program is designed to have plenty of room for such conversations, and we highly encourage you to take advantage of that. And who knows, maybe this will lead to a joint publication about the open avenues in the field, which would be quite exciting. I plan to curate, with your permission, these open problems and put them on our very large blackboard in the next room. So yeah, without further ado, I'm super happy to welcome all of you here. So who is behind this workshop? It is our group here at EPFL that exists thanks to Clément Hongler, who's open-minded to the point of aggregating people that are interested in artificial life. So now our group is essentially working on that full-time and consists of 3 postdocs, me, Vasilis, and Ehsan. So Clément is the one who first suggested that we do this workshop, and thanks to him this has been made financially possible, so thank you. Thank you also to Vasilis and Ehsan for all their help, and a very special thanks to Marie, who's probably in the next room, our secretary, who did an immense amount of work and without whom it wouldn't have been possible. So thank you to all of them. So just a brief organizational intermezzo. So the whole 3rd floor of the Bernoulli Center is ours. Feel free to use all the rooms, especially if you have any meetings online or if you need to take a nap. The place is open from 8 to 7. You will be able to exit the building after 7. You will not be able to enter it again. So in that case, please contact either me, Ehsan, or Vasilis, who have access to the building. So if you have not registered, the registration desk is in the hallway, and there our special guests might find invitations to the dinner, which will happen tomorrow at 7 p.m. We will leave directly here from here. If your hotel provided you with a transportation card, please take it tomorrow. We will use it for the bus ride. Otherwise, just come to me. I have extra transportation tickets to distribute. We also plan to have lunches collectively. Again, our special guests can find lunch vouchers, which are applicable to the 3 canteens that we call Food Lab here. This is where also we have tables reserved for everyone. If you do not have the food vouchers, feel free to explore the campus or join us. There's surprisingly many canteens around here to explore. We plan to record all the talks. If you feel comfortable with it, we will share with you an unlisted YouTube link so you can check whether you like the talk. And with your permission, we will then publish it on our YouTube channel as we did last year, since there are also participants that could not join us from abroad, and they will find that very valuable. And that's it. Enjoy. So last year we received very valuable feedback that it would be interesting to people to also learn what we, the organizers, do. So we're not these mysterious people organizing the workshop, but not telling you what we do. So we will use this morning block exactly for that. We will do a very brief overview of some of the selected works we did, all three of us, and this will be followed by a full talk by Clément Hongler. So since I'm already here, let me start. Again, this will be a very, very brief overview. So the aim is not to go into too much detail, but if you are interested in any of the things we say, please find us. We will be more than delighted to talk about it with you. So when I started being interested in artificial life, as many of you, I just was exploring the fascinating visualizations of cellular automata. And as many of you probably did, the first question I asked is, how can we automatically detect this kind of interesting looking behavior, and where does it belong in the space of all the cellular automata with a fixed, for instance, dimension and states? And to this end, let's say the first ALFE work I did can be called the transient classification of discrete dynamical systems, which was based on a very simple numerical experiment where obviously if you have a deterministic system on a finite cyclic grid, it will eventually enter a periodic behavior. So what I did was just randomly sample initial configurations and measure the average time it takes to enter that loop, and how does that time scale with the size of the grid being increased. And noticed essentially these three simple patterns of behavior, where for these kind of ordered looking systems, as we increase the grid size, the average transient length grows at most logarithmically. And roughly for the chaotic looking systems, the transients grow approximately exponentially. And between these two classes, there is, let's say, this class of systems where estimating the average is difficult because the distribution for a fixed grid size seems to have a long tail, and it is also difficult to estimate the asymptotic growth because from the finitely many data points it is not clear whether it's logarithmic or exponential. But roughly speaking, the best fits for such data is to linear or polynomial curves. And this is actually where most interesting cellular automata that are commonly agreed upon lie, such as Game of Life or Rule 10. So that led to this very rough hypothesis that this interesting behavior happens between these two modes of behavior. But I was bothered by the fact that I cannot prove anything about this, because obviously proving results about the global dynamics on regular grids is extremely challenging and in the worst case undecidable. But after a collaboration with the group here at EPFL, the Statistical Physics of Computation Lab, specifically with Lenka Zdevorová and her student Freya Berens, we realized that if we randomize the C architecture a little bit, we can obtain analytical results about such behavior. Specifically, what you see here is a two-dimensional connectivity grid of a cellular automaton with von Neumann neighborhood. So each cell is connected to its neighbors by an edge, and there is a uniform local update rule applied to each such node. And now instead we can consider a different dynamical system, which is still deterministic, but now we sample the connectivity graph to be a random regular graph. And in this setting, we can study what is the typical behavior for a fixed update rule that is applied to all the nodes uniformly in the thermodynamic limit, as we kind of average over all these random graphs. Specifically, the rules that we studied were somehow opinion dynamics rules, so majority or minority rules, which kind of include some deterministic version of the Glauber dynamics. An interesting class of such opinion dynamics rules are these conformal anti-conformists, which roughly means that if your neighborhood is strongly aligned, you conform to their opinion, but if it's not so strongly aligned, you have the courage to be a rebel and you vote for the minority opinion. And this class of systems with just binary states exhibit two types of behavior. Either typically the activity very quickly dies out, or it looks chaotic, and this depends on the, let's say, region of initial configurations from which we sample. So if we fix this kind of system, we were able to use a new method from statistical physics that was developed by Feja and Plenka, the backtracking dynamical cavity method, but also the dynamical cavity method to analytically obtain these phase transitions in the space of initial configurations, where essentially the behavior jumps from disordered to the chaotic phase. And maybe one last result for this first part about the complexity and phase transitions in dynamical systems is a recent, very simple numerical experiment regarding continuous cellular automata, specifically Lenya, where I was just interested if we explore the parameter space, what kinds of behavior can we obtain. And very simply, if we fix a Lenya system and an initial configuration, and we look at the trajectory of such a system, we can assign it one of the three phases. The stable phase means that within the time that I was able to measure, the trajectory enters a loop. The metastable phase is that the trajectory does not enter a loop, but its center of mass stabilizes around its long-term mean. And the third phase is that neither of the two happens. Roughly speaking, there is some movement happening in the grid. And this led to a result that was visualized by František Dušek, who's here on this exploratory website, which is a very strange rendering right now.
Zoom out.
Okay. Great. So what you see here is a fixed kernel of a single channel linear system. Here is the parameter space that essentially parameterizes the growth function by its mean and variance. So each dot here is just one particular linear system. And as you can see, for various kernels, there is some kind of roughly qualitatively similar shape of this phase space. So what are the phases? This white region means that no matter how we initialize the system, the activity quickly dies out and reaches the stable phase. And as opposed to this is the metastable phase where, irrespective of the initialization, the system or the activity quickly expands and stabilizes in some here, or metastabilizes. And between these two phases is this orange region where the initial where the initialization matters. So for very small patches of noise, the activity dies out. But as we increase the, let's say, size of the noise patch, it switches to the metastable behavior, and within it, essentially all this kind of unclassified or movement detection correlated very well with the identification of solitons. And what's interesting is that these typically occur from initial configurations that are around this phase transition from the order to the metastable behavior. But what is interesting is that this helped us identify movement in systems that would not have been classically deemed as interesting, as many people focus on finding very localized movement in these soliton-like systems or behavior. But another type of behavior where we can see this movement is, for instance, these artificial neuron-like patterns that quickly expand over the grid and start exchanging some kinds of signals. What is pretty interesting, for instance, is that after millions and millions of time steps, they actually synchronize into some wave-like motions. So just to say that Lenya can have different types of behavior, and this is essentially one of the first examples where this kind of self-organization happens on a larger scale than the size of the kernel in some sense. And this in some sense concludes my explorations of the cellular automata space from this dynamics perspective. But as someone with a mathematical background, it quickly became clear to me that maybe the most amenable way to tackle this class is to start studying computational capacities of dynamical systems, as it is often hypothesized that it is exactly this interesting class where non-trivial computation can happen. And what does it mean for a dynamical system to compute? So, inherent to the notion of computation in any kind of system is some kind of notion of simulation. So typically we say that a dynamical system computes if it can simulate some other computational system whose kind of computational power we agree is non-trivial, for instance. And there's two key ingredients to really formalize that. One is, what kind of system is our dynamical system simulating? And the second question is how. So the how typically boils down to having some kind of encoder and decoder, which have the wrong arrows here, actually. So please reflect yourselves around the y-axis. So essentially, if we have some computational system, we would like to encode this input into some configuration of our dynamical system, let the system evolve, and at some point decode the output such that it matches the output of the computation. And the key insight is that these mappings have to be computationally reasonable in the sense that they do not perform the computation of the system, but we have a guarantee that the computation is indeed happening here. So if there's any questions, I'm super happy to answer them during the breaks, but we really should hurry right now. Yeah, this is...
Are the arrows in the correct direction?
Sorry?
The encoding and decoding arrows.
Yeah, those should exactly be flipped.
Okay.
Yeah. Yeah.
That's good.
We're good. Perfect. And the second key ingredient is deciding what kind of systems is our dynamical system simulating. And in the context of cellular automata, this matters. So let's say the more historically classical choice is to study dynamical systems simulating Turing machines. We can call this notion local simulation. That is because the Turing machine at every particular snapshot of its computation only contains finitely many non-blank symbols on its tape. And we would like this to be somehow encoded in our dynamics just within some finite bounded region, which is somehow proportional to the size of this non-blank region. That's local simulation, and in this case we could say that a dynamical system is locally universal if it can simulate a universal Turing machine. So here you see an example of game of life configuration simulating some three-state, three-symbol Turing machine. And as opposed to this, so I will not go into the technical details of how to specify these, but until recently it has been an open problem of how to precise this definition such that it would really take into account all the examples from the literature of Turing-complete systems while excluding pathological examples of trivial dynamical systems simulating some non-trivial computation because we allow these mappings to be too strong. But we essentially did formalize this with Jordan in our recent paper. And let's say the second notion deals with global simulation, where we require our dynamical systems, in this case a cellular automaton, to simulate another cellular automaton in its entirety on the infinite grid, which need not have just finite support. So it is really instantiating the physics of this other system through some, let's say, rescaling and geometrical transformation of the space. So here you see a game of life, where each of these squares is actually a huge supercell, where information is represented in such a clever way that on this larger scale, both in space and time, game of life is simulating a different cellular automaton. Here you see an animation of this. And despite this pattern being finite, it could really work on an infinite grid. So fun fact, this actually is not a different automaton, this is game of life simulating itself. But it could easily simulate other automata too. And it quickly becomes apparent that this second notion is a much stronger notion of universality. So in this case, we say that a cellular automaton is globally universal if it can simulate all the other cellular automata in the same dimension. And an interesting example that came from the 80s is the case of reversible computation or reversible cellular automata, which can be locally universal, but they cannot be globally universal. It is simply too restricting the encoders and decoders for reversible systems to allow to simulate irreversible ones. So this kind of gives us the following picture, which is that every globally universal cellular automaton, since it can simulate some Turing-complete CA, it is also locally universal. but this containment is strict as exemplified, for instance, by the class of local universal reversible cellular automata. So again, this result was known, but a new class of systems that also rely on this interface comes from a recent paper with Jordan Kotler and Clément Anglais, where we study or where we identify some necessary condition that a system has to satisfy in order to facilitate non-trivial self-replication. And we show that there are locally universal cellular automata, ones where essentially, I will not go into the detail, please find me, that do not satisfy this condition. So this somehow debunks the myth that every Turing-complete system can already facilitate non-trivial self-replication. We have examples where it does not. On the other hand, every global universal system does, as it can simulate, for instance, von Neumann's self-replicator. And a very recent result that I have with my master's student, Jonas, who's somewhere here, is a third example of universal cellular automata with zero topological entropy. So whereas Jordan's construction was quite gentle, we somehow just forbid the heads to communicate. For this example, as soon as two heads meet, let's say Turing machine heads that are embedded in the CA space, they somehow explode in kill all activity to ensure that topological entropy does not increase. I think this summarizes the, let's say, selective work that was interesting. But what really kept me the busiest in the past semester, or even longer, was the creation and teaching of the course here at EPFL for master students that we call the Cellular Automata and Models of Artificial Life. And I don't think in this shape or form it really exists anywhere else in the world. So now you can find all the recorded talks on YouTube on our channel Artificial Life EPFL, which is also where we will post all the recorded talks from this workshop. But beyond the teaching, I think the most time I was just writing the lecture notes for this. It was quite a passionate project. It's somehow writing a book that I would have loved to read 6 years ago when I first started being interested in this field. And a huge thanks to Jordan Kotler, who's been contributing to the writing. Essentially, our ambition is to add and enrich the list of these topics that would potentially result in summarizing this in a book. So if you would like to check out these lecture notes, feel free to visit my website. I would be delighted to hear your feedback on this and on suggestions on what topics you think are missing from this list that would have been extremely interesting to us. And it is very exciting that the Jordan will be teaching an enriched version of this course also next semester at Harvard. I would love to talk to you about any of this, and without taking any more time, I will welcome Ehsan.